All right, here we go, guys. This is going to be 8.4 in our notes. This is going to be phase diagrams, section 10.9 in the Zuhmdahl text. We're going to be looking at these images on the right side of the slide here that we call phase diagrams. Every different substance has a different phase diagram. They kind of all look the same in the point that they all have kind of these three little swooping lines that make up the graph. They've got this guy here, and then they've got this guy here, and then they've got this straighter line up here. So they all usually have those three things in common. Right now we're looking at a phase diagram for carbon dioxide, okay? And I just want to point out some important points about this phase diagram. It is showing us the state that the material is going to be in at certain pressures and at certain temperatures. Now carbon dioxide is really interesting stuff, right? Because when we have a solid chunk of carbon dioxide, which we also know as dry ice, right? When we have a solid chunk of carbon dioxide and we put it in a room, it does something really crazy. It doesn't melt, but the heat from the room is absorbed by the dry ice and it actually turns straight into the gas. And if we look at the phase diagram, we can see why this occurs. In a typical room, the atmosphere, the pressure is 1 atmosphere, is right here. Okay? And I would say, you know, a typical room on a good day, not on these really cold days that we've been having, a typical room is about, 21 degrees Celsius. So the temperature is, I would say, like right there on our x-axis. So if we kind of find where those 2 points meet, if I do a little extrapolation here, if I take my 1 atmosphere and I bring it all the way over here, and I bring my temperature and I bring it up here, there it is. I get a neat little point, and I'm going to erase those lines. I'll just put a box around it. I get a neat little point right there, right? Yeah, that is the point, or that is the state at which the carbon dioxide will be at for this particular sample of CO2. So we might ask ourselves, well, what phase will it be in then? Well, it's going to be a gas. And this is strange because normally at room temperature, things, if they're like ice, they melt into water. You know, they always go from solids to liquids first and then to gases. Carbon dioxide doesn't do that. Let me go back here to the CO2 yet. Let's take a look at some other things. You might ask, well, can carbon dioxide ever be a liquid? Sure, if we change the conditions enough. And this would be pretty crazy to do. I've never seen liquid carbon dioxide, but I think I would like that. Let's say we get something that's really, really pressurized, right? Okay, let's say that it is at 72.8 atmospheres. Wow, that's a lot of pressure. And we heat it up to about, well, let's say 20 degrees Celsius again. So that would be like what, right here? Check out where our area is now. If we take a look at our phase diagram, we'll notice that we're in the liquid phase. So if we can get our carbon dioxide pressurized to 72.8 atmospheres, and we can heat it to 20 degrees Celsius, we could have liquid, that's right, we could have liquid carbon dioxide. Yeah, I think that's kind of interesting. Okay. Now you'll notice on the graph that there are a couple of subscripts that are going to need to be explained. If you look at the pressure on the top of the page, it says PC. That's the critical pressure, okay? That's the critical pressure. And you'll notice on the right side of the graph, in the lower right-hand corner, there's a temperature, and it's called TC. That's the critical temperature, and we're going to explain what those are right now. Okay, so this first little blurb here is just telling you what a phase diagram is. And a phase diagram contains 2 points. It contains what we call a triple point, and it contains a critical point. I'm going to go back to that previous graph, and I'm going to show you the triple point, because it's actually pretty easy to find. I bet you can find it if you drew it in your notes. It is right here. Okay, that makes sense, right? It's where all three of those lines kind of meet up. Okay, now the triple point is really kind of a cool thing, because at the triple point, a substance actually exists in all three phases. Isn't that cool? So it can exist in the solid phase, in the liquid phase, and the gaseous phase. Okay? All three states of that particular substance are present. That's neat. And remember, this is for a closed system. So let's pretend like there's no air, no other little things inside of our carbon dioxide system. All right, so that's our triple point. All right. The other point that you may have seen in the graph on the right side of the graph, the upper right side, is called the critical point. let's define some important things about the critical point. The critical point has two facets. Facet number one is the critical temperature. In the lower right-hand corner of the graph, you saw T subscript C. The critical temperature is simply the temperature above which the gas cannot be made to liquefy, no matter how great the applied pressure. At this point, our molecules are moving at such high rates of speed that it does not matter how much pressure we exert on them, they will not come together and intermolecularly combined. Okay? That's the critical temperature. The critical pressure, the second facet of critical point, is the minimum pressure that must be applied to bring about liquefaction at the critical temp. Okay? And you said, wait a minute. We can't liquefy it at the critical temp. We can't liquefy above the critical temp, right? But we can liquefy at the critical temp. So if I can go back to my graph again, we can notice what this looks like. Okay, let's go back here. Here's our critical pressure on the upper left-hand corner, 72.8 atmospheres. Here's my critical temp. So if I want to make liquid carbon dioxide at 31 degrees Celsius, I have to reach my critical pressure, and that's 72.8. Now, if I increase the temperature, okay, if I increase the temperature to 31.1 degrees Celsius, now at this point, it doesn't matter if I go up to 73 atmospheres, 80 atmospheres, 120 atmospheres, or 1,000 atmospheres. It is going to stay in the gaseous phase. Pretty cool. Okay, pretty cool. All right. Now, for these diagrams, you're going to see all these lines. We call these things equilibrium lines, right? We call them equilibrium lines. The reason we call them equilibrium lines is because on these lines, two states exist. So remember what equilibrium means? You know, we talked about Connor and myself being on the balance beam together. Oh, wait, not a balance beam. Seesaw. Yeah, that's right. And we're on the seesaw together, and neither of us go up and down because we both weigh the same. And so these are the equilibrium lines that we call on our phase diagrams, because at that point we kind of have a coexisting of the liquid and the gas for this case. Okay, or for in this case we have a coexisting of the solid and the gas. Okay, good. All right. So this is a really cool phase diagram because it actually is the phase diagram for water. And water is crazy, right? And you see this line here, this little line that's going up, it's going backwards. Oh, crazy, crazy stuff. And water is one of the only substances that has this neat little line going backwards towards the y-axis. So the phase diagram is very similar, has the same types of meanings as what the carbon dioxide one would. This point over here, let me change that. This point over here would be our critical point, critical temperature, so we could extrapolate that down. And we could extrapolate that over. And there we go. Oh, that's a bad line. We could extrapolate that over, and we'd have our critical point and our critical temperature. There they would be. Okay? So it's kind of cool. We can find those things. All right. Now, one really neat thing. Let's check out the X on the line. Let's say we have ice, right? Okay. So we got some ice. We got some solid stuff right there. Okay. And it's at whatever temperature in Kelvin. I don't know. Some cool temperature, right? And we don't increase the temperature. We keep it at the same temperature, but we pressurize it. We had more and more pressure on our ice. So we squeeze our ice cube, and we squeeze it, and we squeeze it, and we squeeze it even more. At a certain point, it's going to turn into a liquid, obviously. Wait a minute. That's crazy. You're telling me that if I got an ice cube or a chunk of ice, and I squeeze it hard enough, it's going to liquefy? That sounds like some Harry Potter type magic stuff. That does not sound right. But think about it. Think about what water does when it freezes. It expands. Oh. And when we pressurize it, what's going to happen? We're going to overcome those intermolecular forces. And we are going to force those water molecules to come closer together. And guess what? Those intermolecular forces will no longer exist. Those little molecules, okay, in a smaller space are going to be bouncing around each other. They won't be able to hydrogen bond. So they'll be fluid again, and a liquid will now exist. That's pretty cool. All right, so let's do a little investigation here. This is the carbon dioxide thing. Now, don't look back at your notes. I want to see if you understand what's going on here. I should have brought a new substance up, but I didn't, so here it is. Okay, we'll have practice on this on Monday. I want to see if you can find a couple things. First of all, the triple point. Can you find it? Let's see if you found it. It is right there, right? That's the triple point. Okay, let's try the next one. Can you find the critical pressure? Can you find it? It is right there, right? Because it leads to this guy. It leads to the top upper right-hand corner of our phase diagram. Oh, by the way, if we exceed this temperature, okay, so if we go higher than this temperature at this particular pressure, we make something called a supercritical fluid. Go ahead and Google that. Check that out. It's pretty sweet stuff. Okay, anyways. Critical temperature. Can we find that? Can we find that? I kind of gave that away. That's right here, right? 31.1 degrees Celsius. Okay, good. Let's see what else. Where fusion occurs. Solid going to liquid. Actually, there are an infinite number of answers to this question. There. Okay, all of those, and all of the little dots in between too, right? That's where fusion occurs. Fusion, that's kind of a weird term, right? Okay, kind of covers both of our bases, right? Because from there to there, that's melting, and from there to there, well, that's freezing. Well, let's call it fusion. Okay, now fusion sounds like things are coming together, so shouldn't it only be this one? You would think so, but it's not. So fusion kind of covers this little area right there. All right, let's see. Okay, so what about vaporization? Vaporization. Again, an infinite number of choices. That one, all the way up the line. There we go. Okay, and vaporization covers kind of both of our bases there. We obviously know that this is more like condensation, right? Gas to liquid, I call it condensation more often. Well, melting point at 1 atmosphere. 1 atmosphere. Where will this stuff start to melt at 1 atmosphere? Trick question, isn't it? Yeah, I hope you found that. So you may have said, well, it's right there. That's not melting, people. At that point right there, that's subliming, because look at what the new phase is that it's turning into. It was a solid, it is turning into a gas. There we go. So, the melting point at 1 atmosphere, forget about it. Ain't going to happen. In order for this stuff to melt, we have to get it to at least 5.11 atmospheres in order for it to actually find and visit the liquid level. That's a cool question. I like that one. How about the boiling point at 6 atmospheres? All right, this one I think we can figure out, right? So 6 atmospheres. Let's see, give me a rough, right there. Maybe that's 6 atmospheres right there. Okay, let's bring that over. Boom, 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 solid to the liquid. There's a melting point. Boom, 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 liquid to gas. There we go. Okay, let's bring that point all the way down. There we go. What do you think that is? It looks about halfway between 31 and 56. That's a difference of about, what, 85? So we got to add another 42 and a half. I don't know. What is it, like negative 11 or something like that? Yeah, sure, negative 11. That sounds good to me. Obviously, we'll be more quantitative on a test. All right, there we go. That actually covers Chapter 10 in Zuhmdahl, which would be the first half of Unit 8 in our class. So, I'm going to give you a critical thinking question. I'm going to skip that slide. I'm going to give you a couple of things here. Well, first question, or only question. As the intermolecular forces increase, I want to know what happens to each of the following. I want to know why. If you can answer these things, you have got this first half of the unit down pat. I'm not giving you the answers right now. We will discuss this on Monday. And I bet some of these things are going to be on your quiz on Monday. So if you're really confused about them, come and see me. Or let's go over them at the beginning of class. Have a great weekend. Enjoy the Super Bowl. I got the Broncos by 6.5. Well, by 6, right?